All right. So again, hello everyone. Welcome. Thank you for joining us in this workshop session. So my name is Elie Kfoury. I'm an assistant professor at the University of South Carolina. I have here with me Samia. So she's also from USC. She's a PhD student. She will be helping us in case any of you is stuck in any of the steps that we're going to be doing in the hands-on part. Um, I also have two collaborators. So Jorge Crichigno, he's a professor also at the University of South Carolina. He's been working with networking for a very long time. And both of us, he's my PhD advisor when I was doing my PhD. So we worked a lot in network programmability and P4 switches, programmable data planes, and so on. Also, I have Jennifer Kim. Jennifer Kim is from the MSCC. MSCC is Minority Serving Cyber Infrastructure Consortium. So Jennifer is with us remotely. Jennifer, would you like to unmute and introduce yourself?
Hello, yes. Hello, everyone. So Jennifer Kim from the MSCC, which is a minority serving cyber infrastructure consortium. Here I am a cyber infrastructure engineer and have been working with these fine folks that you have in person there on a number of things. So with the MSCC, I contribute to the development and implementation of campus supported cyber infrastructure solutions, really to advance data-driven research and education programs on their campuses. And I contribute to workshops, training events, and lots of different things. We are also, what I want to mention is we are also in partnership with Internet 2, which folks may know what that is, and we are funded by NSF. Thank you.
Thank you. Thank you, Jennifer. Thank you for co-organizing this with us as well. So what we're going to be talking about in this session is P4 and DPDK. Just to get a little bit of an idea, show of hands, are you familiar with P4? Okay, some of you are. DPDK. All right. So I'm going to be talking more in detail. What is this about and why it is important and what are the benefits it's bringing? But essentially, we will be able to develop pipelines that will run on CPU cores, right, using DPDK. But instead of using DPDK, which is a library on top of C, we're going to be using P4 to program that. If you're not following at this point, it's fine. I'm going to go into all of these in the upcoming slides. So in this slide here, I'm showing the agenda for today. So we're going to do a little bit of background on P4 and DPDK and P4-DPDK, the intersection of both. Then I'm going to show you a quick video, just demo showing you how we implemented heavy hitter detection using P4-DPDK running at high rates, approaching 100 gigabits per second. Then we're going to do some hands-on labs. So we have three labs. The first one is on match action table, one of the most essential elements in P4. Then we're going to see how, if you would like to compute inter-arrival time of packets, how we can do so in P4. And this is very important for detecting some type of attacks. If you can try to find what is the time between packet I and packet I plus 1. Then we're going to do another lab. Now, this lab here, we're going to show it with physical NICs, right? And we're going to see how we can achieve those rates that we're talking about. So very high speed. And for that lab, we're going to be detecting SYN flood and dropping packets based on some probability that we can configure. Okay. So you see at the top, there is a link here. This is a link for the workshops page. There you will find all the slides in PowerPoint format and in PDF if you'd like access to any of them. Also, we'll talk about it later, but there's a survey at the end. And pretty much everything that we're going to talk about here that you guys would want to have access to is going to be posted on that website. Okay. And Samia, if you can post that on the chat window so that everyone can access it easily that are connected remotely. Okay. I just want to give a very quick overview on the labs that we have. So at the University of South Carolina, we have deployed a cloud that is in partnership with a networking development group company in North Carolina, NDG, and other data centers and universities. And so the idea is we have some resources, CPUs, storage, memory, bunch of resources available, and we would like to use them for training purposes. So what we did was we created these basically virtual labs in terms of content, and then we deploy pods. Those pods will be deployed on different data centers. There's one in South Carolina, one in Idaho, one in North Carolina. We have a few of them. Now, from the learner's perspective, what you guys will be doing, you only need to have access to internet connectivity. So everything is through the browser. No need even to SSH, download keys, install any VM. It's going to be basically just having to log into your account, and then you have access to everything in there. And there we will be running, we have different libraries we've been developing for the past 6 years at USC. Some of them have also some high-end devices, like, for example, Tofino-based switches. These are programmable switches that have a programmable ASIC, so we can also access them and do experiments. We've been using it for research and for teaching at USC. Other universities have been also using our platform to basically train their students. Yes. Yeah, so basically what you will be using is a virtual machine. So it's a Linux-based machine. Now, for the labs that we're going to do, we're going to use a virtual NIC for P4-DPDK. However, the last lab, we're going to do it over a different platform called Fabric, and I'm going to talk a little bit about that. And there we're going to use a physical NIC, right? And we'll be able to see the performance. But sometime in the future, probably a year from today, we should have also these labs that we're going to talk about here available in the cloud and with physical NICs. So every time you reserve a pod, you would have access to a, let's say, NVIDIA Connect X, and you'll be able to run the experiment. Okay? So we talked about libraries. Each library has maybe 10 to 20 experiments. Each of those experiments is probably 20 to 30 pages. I'm going to see an example on this. But we made them in a way that they are very detailed, step by step, so that you'll be able to follow them even if you are doing things on your own without someone teaching you, right? Very straightforward. And there's a link here. This link contains all the libraries that we developed so far. So I'm going to click on it just to give you an idea. And you will see here, I'll have to. So I'm trying to see the screen here, not the Zoom. Just went to so stop share. Okay. Share your desktop Zoom. Okay. See what you're sharing. But I mean, on this one here. That's a good point. Do I maybe exit from PowerPoint? Yes. Okay. So, all right. Thank you. So these are the libraries. This is the link that I was talking about. This is what we will do today P4-DPDK security labs. So we have few labs here, and we're going to keep adding to those. PerfSonar, we have a library on how we integrate P4 and PerfSonar for measurements. Introduction to P4-DPDK, IPv6, cybersecurity if you want to run different types of attacks, how to defend against cyber attacks. We have really a long list. We also have a library on Zeek and so on. So all of those, if you are interested, we can give you access to those, and you can run them on your own and play with all these labs. Okay. All right, so I'm gonna skip these. This is basically what I was showing you. We have on programmable networks, SDN and P4, routing and switching from the basics all the way to advanced topics in BGP, for instance. network monitoring, PerfSonar, SFlow, NetFlow. We have labs on all of those. So again, feel free to reach out if you need access to run those labs on your own time. Okay, is there any question? All right, so let's now get started with the first set of slides. So here I'm going to give an overview on P4 and DPDK. I think I'm just going to use the PDF because PowerPoint is giving some issues here. All right. So what are we going to be talking about in this set of slides? So I'm going to give an overview on packet processing, how it happens in Linux-based machines, then describe a little bit of the overhead associated with packet processing. Then I will introduce very briefly DPDK and then the P4 language. Following that, I'm going to talk about the new project, which basically allow you to write P4 and get DPDK code. Then I will talk about some advances in newer generation of smart NICs and how they can be used for offloading cybersecurity applications. Okay. All right, so in Linux machines, this is what happens whenever you receive a packet. So basically, you have the user space, the kernel space. User space is where your application resides. In the kernel space, you have the NIC driver, and you have memory buffers in there. So the NIC driver would be pre-allocating those memory buffers, and this is where the packets will reside. Now, the NIC will also pre-allocate, transmit, and receive queues ring in the memory. So you will see here, this is the NIC. You would have a TX and RX queues, and those queues will be used to store pointers to the packets in the memory. Okay, so you will see here, this is the RX queue. For example, when you receive a packet, you would have here a pointer that will point to the memory there. And then the NIC will do a DMA, direct memory access, to copy packet from the hardware and place it into the memory. After that, we will generate an interrupt, okay, to say that, okay, I have a packet that's arrived, that now it's ready to be processed. So that happens whenever we receive packets coming on our network interface card. So why is this problematic? Because the interrupt, we all know it can be very costly, right? So the CPU would have to pause the execution that's happening in the user space, whatever process it's executing. Then it will switch from user space to kernel space. So this is a context switch. And there it would schedule the bottom half processing and then return to the process that was executing back at the user space. So another context switch, right? Now, after the CPU has some time, it's freed executing that process at the top. So now it goes back to the kernel space to execute down basically the packet processing. So that's another context switch. Then it would allocate data structure for these packets, and then it would remove the Ethernet header and pass it to the upper layers for IP and TCP and all of the other processing. You might have, of course, a lot of packets, so it's gonna iterate over all these packets in the buffer. So why am I telling you all of this? The problem is there's a lot of context switching, and there's a lot of interrupts happening, and all of these will introduce overhead. Okay, so because of all of this overhead, you are not able to process high packet rates, right? You are limited by a certain number of packets per second because of all these context switching happening. You have dynamic allocation of data structure and the packet copy between the kernel and the user space. All of those are adding to that latency every time you receive a packet. So just to give you an idea, some numbers here. You see here in the table, the first column, you have the link capacity, 10 megabits all the way to 100 gigabits. And if you are assuming that the packet size is 64 byte, very small packet, this is the time budget per packet, right? So you can see at lower rates, this is fine. Okay, 51,000 nanosecond, 5,000 nanosecond. But then when you go to higher rates, 100 gig, in order to get 100 gig per second, right, you have to spend at most 5.12 nanoseconds. Okay. Now remember all the overhead that we talked about, from context switching to all the interrupts that's happening there. And that makes it very hard to get those rates. Okay. So what is the solution? One way to kind of overcome these overheads is to bypass the kernel and place the logic all in the user space. So this is what DPDK is about. DPDK stands for Data Plane Development Kit. The idea of it is that you would write your application running in the user space, and then you would have a NIC that supports DPDK, okay? And now the application would have a driver running on top there that would be pulling packets from the NIC, and then they won't have to traverse any of the steps that we talked about before. So there won't be these context switching, dynamic memory allocation, and all of those stuff. So we're trying to remove this overhead as much as possible in order to get more bits per second and more packets per second, right? DPDK has drivers, we call them poll mode drivers, because they keep constantly polling NIC for new packets and then get them all the way to the application for processing. Now, this is good for performance. The only problem here is that we are no longer using all the functions available in the kernel for packet processing, meaning that you would have to deal with all the packet processing yourself. You'll have to write it there. And DPDK is a bunch of libraries running on top of C. So you need to know C, and you need to be very good at C, know all the ins and outs, and be familiar with all the libraries for DPDK so that you can get started. So it's a little bit challenging to get started. Now, one thing that DPDK allows is also to enable packet processing on multi-core CPUs. Okay, so the idea is within the NIC itself, there is a hardware module here running, for example, over ASIC, and would have multiple queues. So whenever you receive a packet would basically have, let's say, the 5 tuples, source IP, destination IP, source port, destination port protocol. We'll use that information. We hash them so that we can put the packets on different queues. If you have 8 queues, then based on the information you have there and the output of that hash function, you will gonna be sending the packet to basically a certain queue. So with DPDK, what you can do, this is called receive side scaling, or RSS. You can basically configure it such that each queue here will be sending packets to a different pipeline, right? And these pipelines will be running on CPU cores. So for example, here you have 8 queues. You can run these pipelines on 8 different cores. Each core will be just dedicated. It will not do anything else besides processing packets coming from that hardware queue. So you can imagine at this point how much overhead we are removing and how much power we're getting from doing all this processing with DPDK and with the help of a DPDK-enabled NIC. Okay. Now I just want to mention that most of the NICs today, the higher-end NICs, support DPDK, right? So you can go to the DPDK website. There's a list of supported hardware. Pretty much all of them are now supported. I mean, from Mellanox or NVIDIA, ConnectX, Intel, all of them are supported. Okay. This is a graph here showing the performance of DPDK for a simple layer 3 application. So here, the idea is you receive a packet, you look at the destination IP address, and based on that value, you do forwarding out of other port. Very simple, okay? You will see here that they implemented that application, and on the x-axis, you have the frame size, right? From 64 all the way to 1518 bytes. And on the y-axis, you have the packet processing rate and million packet per second. Okay, so here you can see that for 64-byte packets with 12 CPU cores, you are able to get 100 gigabits per second, or the line rate. If you have larger packets, right, or larger frames, you won't be processing as many packets per second because you're going to already be reaching the capacity of the link, right? So you can see here, for example, if you have 100 gigabits per second link, right, you need 8 million packets per second to saturate that link to get 100 gigabits per second. Okay. Yes.
So if you go a few slides above, the point where you have
Yes.
so DPDK is supported. It's not. It's okay.
Yeah, I think I'm not very familiar with eBPF in terms of performance, but from a functionality perspective, they're both competitive, right? The DPDK and eBPF or XDP. And actually, what we will see with P4, if you look at the compiler, it supports backends for XDP and for eBPF. So if you don't want to use DPDK, but you want to use the other ones, it's a matter of changing a little bit in the code to support the architecture there, and it would work. Now, performance-wise, I haven't done any experiments, so I'm not very sure about it. But that's something definitely very relevant. Again, the P4, I mean, I'm going to talk a little bit about it, but the idea was more for programmable switches, but then it evolved that now it supports all these different backends. But yeah, that's very interesting, and would be good to do some study that compares the performance of these different backends. Great. Any other question? All right, so the challenges with DPDK, it's a little bit complex. You need to know a lot of C, and if you want to implement something like a simple software switch on DPDK, that would require you millions of lines of code, literally millions of lines of code. And then if you want to add a feature to that, you have to make sure not to break everything. So it becomes very hard to try to develop your own custom packet processing. Now P4, so P4 emerged as a domain-specific language for packet processing, and it started back in 2013, 2014. The idea was to define packet processing for programmable switches. So you'll get a physical switch, it has a programmable ASIC in it, and you write all the packet processing logic in it. So what can you do there? You can say, well, I want to parse these protocols. I want to define my own headers. I don't want to use, let's say, something following a standard. I want to have my own protocol. You can do that. And with P4, really, I mean, it doesn't know what IP is. You have to tell it that IP, for example, is a header that has these different fields. Each field is this many bits. So you have to tell it all of those stuff. It gives you all the power to do the packet processing the way you want. In addition to that, once you parse your packet, you can do some packet processing like, I don't know, maybe you want to do additions, header modification. If you see the literature on P4, they've been using even to offload machine learning algorithm running directly in the data plane. There's a lot of innovation happening in that space. And we're going to see some examples later. And the idea is you write your code in P4, it's a program, then you send it to a compiler. The compiler will generate a binary. That binary would be target dependent, right? So if you are using a switch, it will generate the binary for the switch. If you are using DPDK, you can generate target code for DPDK, and so on. Once you load it into the target, it will also generate control plane APIs. So let's say you have a bunch of tables that you defined, and you want to populate those tables. It will give you APIs to say, I want to push this flow so that it can be forwarded, right? Or I want to modify the control plane, the data plane element, all from the control plane. So it's all up to you. So how does it work? You see here, this is where the packet arrives. You have a programmable parser. It's represented as a state machine. So you would say, I'm going to start with Ethernet. Based on the Ether type, I'm going to jump to IPv4, for example, or IPv6. And then on top of that, based on the protocol feed, I'm going to jump to TCP or UDP, and so on. So you devise all of that. You program it here. After you're done with parsing, you will go over match action stages. And in those stages is basically where you do the packet processing. Okay, you want to modify the header, you want to store some element into tables. It's all up to you what you're going to do there. Once you are done, you will deparse and basically send the packet out of the wire. Okay, so here basically summarized as what's supported here, right, in the program. What are you going to parse? what are you going to do to the packet? Okay, or to the state of the device, because we will see that you can also store in registers, right? And then you want to forward that packet. So you do transformations on the packet. This is an example of a program. I'll skip this because we're going to see it later in the exercise. So why P4 for CPU? Because as we said, DPDK can get very complex when writing large programs. But at the same time, basically all these functions that we saw, parsing, packet transformation, deparsing, that's same for packet processing, whether it is CPU or switch or SmartNIC, we're always going to be doing basically the same. For example, we said the switch would require millions of lines of code with C and DPDK. For P4, you can write it in 5,000 lines. So it's much smaller. And it's only smaller really because P4 was designed for packet processing. It's not a general purpose language for any system, right? These are basically a table. This is a table showing the attack. If you want to defend against some of these attacks, how many lines would take you with DPDK and with P4? Although you can do things much lower with P4 as well, or much higher in DPDK. But yeah, it will allow you to do things much easier, for sure. All right. So what we're going to be doing basically is combining the flexibility of P4 and then the performance gains of DPDK. And this is the project called P4-DPDK. You write P4 code, you generate DPDK code, and then you'll get the benefits of the performance of DPDK. That's the whole idea. How it works, you start by writing your program, you call the P4C, P4 compiler, and then it will generate a file. It's called a spec file. We're going to see it in the lab. And that spec file is going to be used by a pipeline library. This is all part of DPDK to generate a C code. You compile it with a C compiler, you get a shared object, and then you deploy that program. So you as a programmer, all you have to do is write the P4 code. Everything else is going to be running for you, right? And based on that program, the library will basically transforming those match action tables that you write in P4 into the right data structures with DPDK. So another added value is that with DPDK, you might not be writing the best way to represent a certain network functions. With P4, because it's very limited to what you can do there, you are sure that you are getting basically a better representation later on in DPDK. What are some supported features? You can do basically exact matching on tables, longest prefix match, wildcard matching, a lot of features that previously were supported for the switches have been, progressively being added to P4-DPDK. The runtime interface, registers, counters, meters, all of these elements, you can use them. And recently also software NICs. So this is what we're going to be doing because, for training purposes, instead of having physical NIC for everyone, we're going to use it just to learn. And then that same code with no changes at all, you can now port it to a device that has a physical NIC and get the performance. So from a code perspective, there's nothing different from writing for a soft NIC versus a hardware NIC. And there's a vision, it's been mostly in academia, that they want to use P4 across the network stack. So not only for physical switches, but also for the new generation of NICs, smart NICs, as well as the CPU. So it's basically you write P4 for packet processing end-to-end for everything in the past. That's the vision, although I don't know how much time we're going to need to get to that vision. For example, you mentioned XDP, eBPF. You see here, so P4 does support those, and this is what you will get. That's basically the idea. Okay, so not sure why this is happening. Okay, so basically, as we said, the idea is to try to use that P4 program to generate for different targets, right? And because P4 was designed for packet processing, they saw that, okay, why do we want to reinvent a new language for these new smart NICs that have emerged lately, or, processing on CPUs? So we want to make sure to use that same language for pretty much all the packet processing, any data path. And that's why P4 stood up, because it wasn't just restricted to the switches by a company that, later on did not even continue with the switches that they started with. Right? So for those online, we're sorry, we're having some technical difficulties. We're working on them.
It should have still been.
Okay, thank you. Is there any question before we proceed? All right, so I just want to talk a little bit on about the new network interface cards, because I think it's something that is very, very interesting nowadays, and they're becoming very popular and very powerful. So traditionally, a network interface card is very simple. You have the ports, the traffic come to the port, then you have a DMA engine that transfers the packet to the server, and you do everything there on the server. That's the traditional first generation of NIC. Then we got to a newer generation of NIC. We call it offload NIC, because now there's some hardware-based accelerators here where you can do something like checksum computation, the TCP offload engine, a bunch of things that are important for packet processing. Instead of doing things in the software, let's just offload them to the hardware. Most of the NICs today are offload NICs. Now, recently, there's a new generation of smart NICs. Those NICs have a little bit more features, in the sense that now you have a programmable pipeline running within the NIC itself. So that pipeline that we were talking about for DPDK or for the physical switch, the NIC itself can also have a pipeline. These are very recent. In addition to that, you'd have CPU cores running within the NIC itself. So you're able to do all the management of the NIC, run, for example, the IPsec control plane on the NIC itself, do complete isolation from the host. And in addition, you have some domain-specific accelerator. Give you an example, you want to do encryption and decryption. You don't want to do it in the software, you can offload that to the hardware. You get much, much better performance. So they come in very different flavors. For example, some vendors use FPGAs, some vendors use programmable ASICs, some vendors, it's all CPU for custom packet processing. So there is no single design for those, but they're becoming more and more popular, especially in cloud environments, because they're allowing the operators to offload a bunch of things to the NIC, release the CPU from processing the infrastructure task, and then make more revenue, basically, because now the free CPU cores are using for the VMs. So that's a very interesting new area of research, and also it's used a lot in production. Pretty much all the major clouds that you have heard of are using smart NICs. Yes.
So in essence, we're going to smart NICs
With
where
yeah, kind of, yeah, in the sense that you are now programming things on the card itself, right? Again, it has a lot of added value for performance reasons, for security reasons, because now you are isolating, and it's also used for storage. Some machine learning algorithms are being offloaded there, so there's a bunch of new exciting areas of research. So give you an idea on cybersecurity applications, if you have IDS or IPS functions, something very simple like bypassing traffic. So you are receiving some traffic, you are not interested in doing deep packet inspection on that traffic, you want to bypass it. Traditionally, this was a function implemented in software, but now you can offload that bypass function to run in the hardware, right? In the ASIC or in the FPGA. What is the added value? You can see here some performance results. This is for Suricata. They implemented the bypass function in the hardware. And you can see you can get the 400 gig, the line rate of that NIC itself. It's all happening in hardware. Traditionally with the software, you will get much, much smaller, much lower performance. Another added value is that the CPU cores on the host are barely now being used, right? Because everything is happening down on the hardware itself. Whereas if you look traditionally, you have to consume CPU cores to be able to do such function. Also, this is available with next generation firewalls from Palo Alto. You can see some results that they have there. Another area is encryption, pretty much any cryptography function, right? So symmetric, asymmetric encryption, true random number generator, hashing. So if you see here, for example, what you have with the kernel TLS in the software, right? And then you have the kernel TLS uploaded to the hardware, you will get the line rate, very similar to the plain text TCP. That's how much performance you get when you offload things to the hardware. All of these are becoming now more popular with these NICs. Also, IPsec, you can have the encryption of IPsec offload to the hardware, and then on the CPU cores of the NIC, you can run the control plane of IPsec. So it's really becoming like a new kind of design where you get performance, and then you release your CPU at the top for your business application. Nothing has to do with infrastructure tasks, basically. So in summary, there's a lot of advances happening with packet processing. We're going to be doing some activities on P4-DPDK, and we're going to see some code, how we can compile, deploy that code, and then at the end, we're going to see some performance results. And as we said, there's a shared vision in the community to make everything P4 programmable, and that includes also the new generation of smart NICs. All right, is there any question? All right. So before we get started with the hands-on, I just want to show here a quick demo. So this is an application that we did on P4-DPDK. This was Samia's work. Again, she's a PhD student. She just started. We are trying to use P4 and DPDK for scalable heavy hitter detection. Heavy hitter is simply a flow that is transferring a large number of packets at a given time. And this is the setup that we have. So the idea is that you have in the middle here the heavy hitter detector. There's a physical NIC, and then okay. So sorry about that. I don't know what's happening with the display. Yeah. Actually, yeah, probably. Should we try on a different laptop? Maybe let's.
So there we go for now. Take it real quick.
Thank you.
Go ahead and.
Okay. All right. So again, what we have here is a physical NIC. This is the NVIDIA Connect X6. It's this is where we're gonna be running the heavy hitter detection. It's gonna be using DPDK, and we're gonna write the program using P4. And the scenario is as follows. We have two servers. One will be generating background traffic. So essentially, this traffic would have randomized 5 tuples, right? So that you kind of emulate different flows. Whereas the other device will just have the same 5 tuple, meaning that you are sending from a single flow. You are pushing data here. So we're pushing here 1 gigabits per second. And the idea is to detect that flow among all these randomized flows that are coming at 100 gig. Once we detect it, we want to block it. So we use DPDK packet gen, which is a tool to generate packets. We're going to see later on in the lab, but it will allow you to specify the 5-tuple information, packet size that you want. If you want to randomize, the MAC address, whatever you want. I mean, when you construct the packet, you can decide how it looks like. All right, so this is the scenario that we have. So for the way we can test that, right, we're gonna see all the packets that are leaving the background generator, right, background traffic generator, will come back. Okay, so we know how many we pushed, and we know how many we got back, and then we can see how many of those were lost, right? Whereas in the heavy hitter, they're gonna be pushed and then blocked. So really, that heavy hitter detector program, in addition to doing the detection, it's also implementing a packet reflector. So it just reflects the packet where they come from. Okay. So this is what we did. We wrote the code here, and then we deployed it over up to 8 CPU cores. I'm just gonna skip over those because we described them in the slides. And then we implemented that over Fabric. So we're gonna talk a little bit about Fabric later, but it's a national test bed for research and experimentation and also education. So you are basically capable of creating a slice where you say, I want a node in South Carolina, a node in California. That node would have this many CPU, this many GPU, that type of NIC. And then you will SSH into them and do all the configuration that you want. Okay, so here, for example, we used all different servers in a single site. This is in Seattle. And then this device in the middle, the server in the middle, is doing the detection and all the packet processing. Server 1 and server 3 are just pushing data. All right. So we ran now the pipeline. And here you have 2 screens. On the left, you have the background traffic generator. On the right, you have the heavy hitter. So when we start, you can see here we are pushing around 100 gig, 99 gigabits per second, and then we are receiving them back. So on the right, you have the TX, on the left, you have the RX, meaning that all the packets got to the CPU there and got reflected, right? Whereas for the heavy hitter, we are pushing some packets, they got there, and now we are no longer receiving anything coming back, right? So this means that here we are able to identify this heavy hitter among 100 gigabits of traffic being pushed from another device, and that other device is randomizing the 5 tuples. So it's as if you are getting packets from a lot of different flows. You are still able to identify the flow that basically was contributing most compared to the other flows. Now, technically, it's not very straightforward in the sense that you cannot keep track of every single flow and have a counter dedicated for the flow. Why? Because you're going to end up having very large registers, and this is something that does not scale that well, right? So instead, you would need to do or use some probabilistic data structure. Here, we use something called count-min-sketch, just to be able to track these counts in a scalable way, basically. But again, the idea is just to show you that the programs that we're going to run later on with the software NIC, when you deploy them in a device with a physical NIC, you will be able to get those rates, as long as you are not doing a lot of processing, right? So you have to make sure when you write your code to write it in a way that it's doing the job, but it's not really doing it in a way that a lot of processing is happening. Okay, so it's up to you how you devise that. Okay. Is there any question? No? All right. So now we have 10 minutes before the break. So what we will do, we're gonna start by going to the hands-on labs. We're gonna make sure everyone is able to log in. And then after we come from the break, we can start with the actual hands-on lab. All right? So go back to the agenda. We will do the lab number 1, Introduction to Match Action Tables. So I will describe about Match Action Table, but let's just, for now, all log into the system and make sure that we can start doing the hands-on. So here is where you will find the link to access the platform. So I will leave the screen here for a little bit. It's netlab.cec.sc.edu. Okay. For all of you who registered to this workshop, we already created accounts for you. Okay. So the username that you will use when you log in, this would be the email that you used when you registered. And then you have a temporary password here, NSF 2024. Once you log in, it will ask you to change the password and select your own. Okay. Now, for those of you who are joining online, we also have accounts for you. If you registered, you should be able to do so. If you are facing any issues, please post on the chat window, and Samia here will be able to troubleshoot and make sure that you can get into the platform. Okay, so I will leave this for a minute or two. And please, if you have any question, just let us know. Samia will be going there to help you out. It's not possible that you can go the question. Yeah, so see consoles, that's awesome. Then you have here the right. So there's a yes. All right, so let's let me see, what time is it? We have 5 minutes before coffee break, so let me just go over after you log in and you change your password, what we're gonna do, and then we're gonna go to the break. So once you log in the first time, it's gonna ask you to change your password. You enter your password here. After that, it will take you to the dashboard, and you will see nothing there, just empty reservations. You click on New Lab Reservation, and then Schedule Lab for myself. Okay? Now, after that, here I provided already 5 courses. So each one of those is a lab library, okay? And you have access to all of them for 6 months. So you can do all of those later on. And if you need more than 6 months, just shoot me an email, we can extend it. There's no problem. For this session, we're gonna do the P4-DPDK security. So we're gonna click on P4-DPDK security. And then we're gonna do lab number 4. We're going to start with that lab. So click on lab 4. Now here is where I need your attention. Each one of these blocks here is a pod, and a pod is basically a virtual machine in this case. In some cases, it can be multiple virtual machine, but now for this lab session, one virtual machine per pod. And there's enough pods so that all of you can log in at the same time, right? Now here we are seeing 4 of those pods. But here you see also a button where you can click on it, and then you'll see even more pods. The red line is showing you basically the current time. So this is just a scheduling system. You're saying, I want to schedule a reservation to run this experiment. What we will do is we're going to click on the red line so that we say, I'm going to schedule the session right away to start right now. Once you do it, here it will show you a calendar where you can specify the length of your reservation. For example, here it's showing 44 minutes, but you can put it like for 2 hours, right? And I'll advise you to do that. Even if we end up finishing earlier, we can simply just cancel the reservation. It's not a big deal. And pretty much that's it. Once you are there, now we can start with the lab. So if you have any issue following these steps, just let us know. And I will be doing them again because I will be going over the lab with you guys. Sorry, I overheard Stanley because we work with Stanley.
Last year, we were sorry, the cybersecurity policy already. Last year's annual substance. So we know exactly. We're using the cybersecurity. It also has when you're going to service on the receiving. Yeah, that's all there is. So, well, we can send you
So for those of you who are joining online, we have now a break. We will be back at 3:30 p.m. and we're going to start the hands-on session at 3:30. All right, welcome back. So we're gonna be continuing our session, and we will be starting with the hands-on part. If you're still having any issue logging into the system, please let us know. We will go there and help you so that you can do the hands-on lab with us. So I'm gonna be for this first lab, I will go into a concept called match action table. And match action table are fundamental units in a pipeline, because this is where you will be defining basically all the packet processing actions that you want. And at the same time, this is where you can push rules so that you can match on some flows. For example, let's say you want to do forwarding, you would have to create a table that says, I'm going to do forwarding based on, let's say, IPv4, destination IP, and then I'm going to take this action, which is exit out of interface 2, right? So all of this stuff happens within a P4 table. And they are implemented after we are done with parsing, right? So we are done with the parser implementation, you get into the match action pipeline, this is where you implement the table. And we're going to see an example of that very soon now. So when you define a table, you have to specify what are you going to match on. Is it destination IP? Is it destination MAC? It's very arbitrary, right? We know that historically, I mean, you can do matching on destination MAC address, let's say in a switch, or in a router, destination IP. But with P4, it's up to you to decide where you're going to match on. And then what are the actions associated with that table? Do you want to drop the packet? You want to forward? Do you want to increment or decrement the time to live? You've specified in the action. And what is the size of the table? Are you creating a table that will hold 1,024 entries or 65,000 entries? You have the option to specify that. So this is how it looks like. You have a table. From the control plane, you would populate that table, right? And then whenever you receive a packet, you would look at the headers of that packet and as well as some metadata information and use those to construct a key, right? So for instance, if I'm creating a table for forwarding using IPv4, my key would be the destination IP address that I get from the packet headers. This would be the key here. The action is like a custom action that I created called IP forward. And then the data is what is the output port that you're going to take. For example, egress port number 4. Okay. And then, of course, the control plane will be used to populate these entries. Once you have a hit, let's say this first entry here hit, because that's the destination IP that I have in my packet, the action code will be executed. And you can have there, it's like a C function. So you can have multiple entries within that action code. For example, here we're assigning the output port, the egress port to 4. We are decrementing the TTL. We can do pretty much anything that you wanted there. Okay. So for this lab, this is our topology. We will have this pipeline here. That's the device in the middle, the P4-DPDK. And then we have two hosts here that are network namespaces, virtual hosts. Okay, they are connected to the pipeline. And the idea is to create a match action table running within the P4-DPDK. And that table would allow us to do forwarding between these two devices. Very simple, just to get started. Okay. So with that, I'm going to now switch to the hands-on. All right, I will log in. So for those of you who are just logging in, after you log in, it will ask you to modify your password. I'm just going to create a quick password here. And then we schedule a new lab. So schedule lab for myself. These are the courses available. Again, they're available for 6 months. We can extend as well. And also, if you want other libraries, we can add them to you as well. Just shoot us an email. So we're going to do the P4-DPDK security and then lab number 4. So you can see here, there's already some reservations. Some of you already started their reservations. I can see them here. But we have enough pods so that all of you can run the experiment at the same time. So I will click here on the arrow to explore more pods, and I will just find one that is empty. Click right on the red line so that I will create the reservation right away. You can specify the time here for how long you want it. Submit, okay. Then you would see here your reservation in the main page. You click on Enter Lab, and now in the background, there's a new virtual machine with all the dependencies, all the software, everything that is being created. You can start using it right away. You don't have to use SSH or anything at all. And here you can see this is our machine. So if I want to go to my machine, I will click on Client. That will open my Linux machine there. I can do all the experiments. Okay? Now, what is the activity that I'm going to do? So you see here at the top left, there's content and there's client. What I usually like to do, I click on the arrow next to content and then undock. Okay, so that I put it on a separate window. And then on the client, I do the same. So now I have two windows, one that has the virtual machine and one that has the lab content. I will place one of them to the right and the other to the left. And now basically I have my VM on the right. I can do the step, and here I have the manual. So regarding the manual, you will see every lab. It has at the beginning overview, objective, credentials. If you ever use a password, like you want to run a command with high privilege and you want to enter a password, all the information would be at the beginning. The roadmap. The first section of all the labs is more about the background information about a topic. Like here, it's about match action table. So we're talking about what is a table, what is a match key, and all of the stuff that we described in the slides. Okay. Now, starting from section number 2, this is where we start with the hands-on part. You will see that the labs are very detailed in the sense that every single step that you have to do has a screenshot so that you can exactly do it and not be lost while you do the experiment. So it's all about really following the instructions, and it's designed so that you can even do all the lab without having someone to teach you how to do it, right? So, all right. As you can see, I'm going to start here with this step, 3.1. It's telling us to launch a Linux terminal by clicking on the Linux terminal icon on the taskbar. You see the screenshot here, and that's the system, right? So I'm going to click on the terminal. This is going to open a Linux terminal where I can start issuing commands. And then the second step is to open the editor. So we are using Visual Studio Code, and it has an integrated terminal, so we can compile directly from there, basically. It's just, you can use any text editor. You can use Vim, Nano, it doesn't matter. Now, for each of the lab, we have a directory that contains some starting code or some information that are relevant for every lab. So here, we are doing lab number 4. So I'm typing this command, code P4-DPDK labs, lab 4. This would launch the Visual Studio Code. You can see on the Explorer here, we have all the files for that lab. Okay. So in the steps, they're telling us to start by opening the control.p4 code. But before I do that, I just want to show you really quickly the structure of a P4 program so that you get a whole idea about all the parts in it. This is where your code starts. This is the main file, right? It's like a C code where you have other files and then you have the main file. Here you start by including the libraries. So there's core.p4. This is the basically the library for the P4 language itself. Now, the second line, this is for the portable NIC architecture, PNA, and that's what DPDK uses. Then you can see here we have some includes for custom files that we created. And then finally, we instantiate that pipeline by writing PNA NIC, and then we list all the control blocks. This type of code will be fixed. Really, you don't really need to change it that much. What you would care about mostly is updating the header file to define the headers, the parser, the control, and then if you want to do some custom deparsing, you can update the deparser. But this is just like calling everything. That's the main file. Now let's see the parser, how it looks like. So you create here a parser, right? We are calling it my parser. You start with the starting state. So that's the state that will be executed as soon as the packet comes. What do we have in this state? This is a state machine, right? So we are calling to basically transition unconditionally. There is no condition. I'm going to another state called parse Ethernet. Now note that parse Ethernet is also user-defined. The P4 does not know what Ethernet is here. Okay, so we created here a state that we called it parse Ethernet. Within that state, we need to extract the headers from the packet. So I receive the packet, right? I extract the headers. Now they are part of a data structure that I can use later on in my P4 code. And then I want to see, maybe I want to parse now on top of it is IPv4 or IPv6. Typically, in order to know what is the next protocol, you would look for the ether type field in the Ethernet, right? So here I'm saying transition, select on the ether type. If it is type IPv4, jump to the IPv4 state. If you want to parse IPv6, you create another state here and then you jump to IPv6. So this here is like a switch statement in C, right? So you match on the value and then you jump to the right state that you want. And also we are parsing the transport layer here. So based on the protocol field in the IPv4, if it is TCP, I jump to state parse TCP. Now you might tell me, so how did it know what Ethernet is or TCP? All right. So there's a file called headers, and this is where we are telling it what is Ethernet, what is IPv4, what is TCP, and so on. So Ethernet, you have destination MAC, source MAC, ether type. You can do type defs so that, for example, you don't have to write bit 48 every time. Yes.
So,
yes. Uh-huh. Right. Yeah, so what changes between one NIC and other is the poll mode drivers, the PMDs, right? Now, from a programming perspective, it doesn't change that much. However, in some cases, you have a NIC that supports like a crypto accelerator, one that does not support crypto accelerator. So this is where your code would change. Now, from P4 perspective here, is going to be the same for any NIC because we are not using any accelerator beyond just the packet processing. And the NIC itself, I mean, remember, this code will run at the CPU host. However, there is a way you can run this code on the CPU cores of the NIC because now smart NICs have CPU cores, so you can also run it there if you like. Okay? Any other question? All right, so IPv4, you see here, this is how we are saying all the fields. And where are we getting those from? I mean, you look at the specification of IPv4, you get, okay, you start with 4 bits for the version, the IHL, and so on, and same for TCP. So this is where you define pretty much all your headers. And finally, you have to have a struct to combine them. This is where you're saying, I want my headers to support this and this and this, right? So Ethernet, IPv4, TCP. So with that being said, now when we go back to the parser, when I say here packet.extract header.ethernet, I'm filling that structure that I just showed you here, right? Based on the sizes that I define in the header. So because Ethernet here has 48 bits for the MAC, 48 for the source MAC, and then 16-bit for the ether type. So you add all of those. This is how much you are extracting from the packet and placing in the structure. Is that making sense? All right. After right, so you can think of this as a tape device. You start from bit 0, okay? Now, I'm saying here extract header Ethernet. So if I go to headers, Ethernet, right? If the way I defined Ethernet is with these fields. So these fields, you can add them up, right? But by the way, this is just a type def for 48. So you have 48, 48, 16. So this means that I'm extracting 48 plus 16. I'm placing them in the Ethernet. Okay. Exactly. And now my tape is here. So when I start extracting again, it's going to continue from where you are. Okay. So the control basically is where you can do all the packet processing logic. So you are done with the parsing. Now you move to the control. So what are we going to do here? We're going to start by creating actions for forward, for drop, and then create our table. So what you see here on the left-hand side, whenever you see a red box here, it means that this is some stuff that you have to type, right? So here, for example, I'm going to type this block of code to create an action called forward. that action will get a parameter, a port ID, and simply it will call a function that is predefined that would basically send the packet to that specified port ID. All right, so going back here. All right, so I'm gonna create that action. So action forward port ID, and then I give it a variable name, this port ID. And within that, I'm gonna call send to port and give it the port ID. Now you might tell me, where is this port ID coming from? Eventually, this is gonna be associated with a table. And when we populate the table from the control plane, I would say that if I see this destination IP address, I will take that port number. So these will be filled later on in the control plane. Okay? Please feel free to stop me if there's anything that you have to ask a question on. Okay? So this is here kind of similar to defining some functions in C, right? We are not calling anything at this stage. We're just saying this is how the forward action looks like. Now I'm going to create another one for the drop action. The drop does not accept any parameter, but it simply calls a predefined function called drop packet that would cause the packet to be dropped. That drop packet is part of the architecture, which is if you go to the yes. So send to port and drop packet are predefined. All right. Now I can start by creating my table. So my table here, I'm going to simply call it forwarding, because that's the job of this table, to do packet forwarding. Okay. Now, remember that when you define a table, you have to specify what is the key that you would like to match on. And that key can contain one value or multiple values. So you can say, I want to concatenate, I want to match on the destination IP and the source IP, right? I want to match on this 4-tuple information. This is possible. Okay, so in my case, I'm going to write here key equal header.ipv4.destination address. So here, I'm getting the header. So this is the header that I parsed, right? Because I had the parser at the beginning, I filled this header with the information. So there's already something called IPv4 in it that I parsed initially. And then within that header, IPv4, there's a field called destination address. So this is the destination IP, basically. Now for the key, you'd have to write after colon and then specify what is the match type that you want to do. You can do exact matching, meaning that I'm going to match exactly that specific IP address. Or you can do longest prefix match, LPM, meaning that I want to match an IP that's part of a subnet. You can do range matching. I want from, let's say, if the value is from 10 to 1500, I want to match it. You can do ternary matching. So we have different match types in P4. Here, we're just going to use exact matching, very simple. And by the way, all these concepts that I'm talking about, there are labs on them. The goal here of this, interactive session is just to give you an idea how to get started, but you have all these labs and you can run them on your own as well. All right. So now I define my table. I have a key in it. The other thing that I have to add to my table is what are the possible actions associated with that table? Because every table has a list of actions associated with it. You can have multiple tables, a lot of different actions. So my action here, I have 2 actions, those that I just created, forward and drop. So I have to put them under the available actions for this table. So forward and then drop. Okay. Next, I have to specify what is the size, meaning that this table, how many entries it can hold at max, right? So the size I'm specifying here is 1024. You can go higher than that value, meaning that I can support at most 1024 different destination IP address that I can match on. Of course, this is not very, realistic. In a realistic environment, you could have longest prefix matching and create bigger tables, but it's just all configurable. It's up to you to define how you want to process your packet. Is there any questions so far? Are you able to follow, or am I going too fast? All good? Perfect. All right, so that's it. Now I have my table, right? I just defined the table. Notice that I didn't call anything. I didn't invoke. In C, you create a function, then you have to call that function, right? Here is the same. You have, whenever you have a control block, like here we called it our main control block, you have to create an apply. And essentially, this is where you start invoking your tables, your actions, all the packet processing. Everything before that was just definitions. Now I'm calling them. So what I'm going to do here, I want to activate that table. I want to apply that table. However, that table assumes that the packet that I got is IPv4. What if I got IPv6? I cannot just apply the table like that. So one way to do it is to add a condition. And that condition would basically check if the parser really reached that state that parsed IPv4. Okay, so if you write an if statement here, and you say header.ipv4.is valid. So is valid also is a predefined function. It's just basically a flag that will be set only if the parser got to that header. So again, this if will be executed only if my packet that I'm currently processing has IPv4 header. If it is IPv6, this will not be satisfied, this condition. All right, so if it is valid, I want to call my table. So what's my table name? It's forwarding. So I write forwarding.apply. That's it. Okay, you can also have an else statement, and you can have else if, very similar to other languages, and then have an explicit drop statement, meaning that if it's not IPv4, I'm going to drop the packet. Okay. But as you can see, I mean, the beauty of P4 is that it's all up to you to define what you want to do with your packet. Okay, the switch can be a router, it doesn't have to match on destination MAC or destination IP. You can do, all of it is custom up to you. Any questions so far? All right. Well, that's pretty much it. This is what you need, for example, to implement forwarding based on IP, destination IP. If you want to write this in DPDK, that would take you way longer programs, right? Now, you have to press Control S just to make sure to save that file. And then I will start a terminal. I will do the compiling from a Visual Studio itself. But, you can do it from the terminal. It's the same. So I'll click on New Terminal. That will open the terminal right in the directory where I am, where all my files are. And from there, I will invoke the compile. So to compile, I will call P4C. P4C is P4 compiler. But you see here it has -DPDK. So P4C-DPDK is the P4 compiler for the DPDK backend. XDP, you write P4C-XDP, right? Other targets have different backends. Now, the backend can be implemented using different P4 architectures. Here, DPDK follows the portable NIC architecture, which is just basically how the blocks are connected, the parser, the match action pipeline, the deparser. So you have to specify that by writing --arch for architecture, and then PNA, portable NIC architecture. The input to that compiler is the main file, because in the main we are invoking everything else. So it's main.p4. And the output -o is a file that has the extension spec. And I will show you how does it look like. So when you write that command, if you don't get any output, it means that you don't have syntax errors. You're good to go. If you have syntax errors, the P4 compiler is pretty decent in telling you where your error is. It will tell you the line, and you will go fix it. Now you can see here in the file explorer, right? I compiled my file, so now I have a new file that is a spec file. And if you look at it, this is simply, it looks like assembly here, right? Because that's what this DPDK pipeline library processes. In fact, you can write this spec file without using P4 at all, and then run it on DPDK if you want. All right? If you try to follow it, it's basically the logic that you wrote in the P4 code. So you start by, you receive the packet, you extract Ethernet, you jump if equal to that value, and then it's assembly, essentially. All right? Now, we have that spec file. If you remember from the slides, we said that after we have the spec file, we have to generate the C code, compile the C code, and then deploy it in our CPU core, right? So what we will do next, I'm gonna open my terminal. I will go to super user. So when it asks you for a password, simply it's just password, all small case. We just made it easy so that, you know, we don't have to type a bunch of things when you are running the lab. Then I will move to the directory where my lab is. So it's P4-DPDK labs, lab 4. Yes. Oh, sorry, there's a. Sure.
Please remember. That's your.
Thank you.
Yeah.
Yes.
So we don't expect
Mm-hmm.
to see the instructions from assembly.
Right.
Take the people. People assembly.
That's a great question. So we will see when we run the program. I mean, DPDK in general, right? You can activate a flag when you compile it so that you say, I want debugging enabled. So when you have that, and we have it for those labs, you should be able to see when you have a table that is hit or a miss, which action is called, which state is parsed, and so on. So you will see all of those, but you're not going to debug it with assembly. You're going to debug it with P4, although it's still not very, you know, it's not very powerful in a way that you can get everything from the P4 code. Sometimes you have to go and look at the spec file. But debugging is enabled. Now, keep in mind, when you compile it for a real deployment, you have to disable logging. Otherwise, you're not going to get the performance. Okay? It's like any other, you know, program, right? That's a great question. Any other question? All right. So now I will call a script called run pipeline. This is simply a script that if you ever ran a DPDK application, you might see some of the stuff here familiar, right? EAL, detected CPU cores, NUMA nodes, and so on. Because this is really actually running, we are running that DPDK pipeline. But for that pipeline, I'm passing to it the spec file that I just generated from my compiler. So I'm running the DPDK pipeline with the output of my P4 compiler. Is that making sense? Yeah? All right. Then there's a bunch of things happening here. So there's a file called, it's a CLI file, right? I will show you here how it looks like. This is basically something that you would configure once and then that's it. But if you want to create ports and attach them to your pipeline, you create here a new device. You give it a name, and then you pass out a bunch of parameters that are DPDK specific. We're not going to go over all of them. Now, in a real deployment, you have a physical NIC. Instead of having a TAP, which is a virtual NIC, you can have a PCIe address here, something like, you know, 070000. It becomes a physical device. And we're going to see an example of that later. Okay. Now, in this script, we are also adding to the forwarding table rules.txt. This means from the control plane, I'm pushing rules to my data plane. And those rules are written in a file called rules.txt. You can see here it's match on the destination IP. We just have to encode it here in hex. Which action you want to call, and what is the parameter for the action. So match on the IP of host 1. If yes, forward it out of port 0. If we match on the IP of device 2, we forward it out of port 1. If you have multiple action parameters, you can keep listing them next to each other. Okay, so this is how we are now from the control plane defining what entries do I want in my table. Okay. And then finally, you enable that pipe. One thing to notice here, I'm going into a lot of details. You don't really have to know them because most of the time you just have the pipeline written and then you run it. But it's important to understand some stuff here. For example, this last line, we are enabling the pipeline on thread 1. If I want to run it on multi-core CPUs, let's say I want to run 8 pipelines just to make it faster, to distribute the load on 8 CPU cores. You write here pipeline 0, pipeline 1, pipeline 2, and you enable different threads. I'm going to show you an example also later. Okay? Any question? Exactly. You do pinning here. It has just the job of processing packets, nothing else. That CPU core will be reserved. No, there's no. That's why you get performance with DPDK. You don't have this context switching. You are pinning, and then you are getting the packets without going over the kernel stack. So you are basically resolving all these overhead concerns that I talked about in the slides by doing that. And this is DPDK specific. It has nothing to do with P4. The only thing P4 is doing to us here is just help us with the code that we want to translate it to DPDK later. All right. So I ran the pipeline. I'm going to open a new terminal here and basically go to super user mode, go again to my folder where my labs are. And from there, this is what I just showed you regarding the rules, right? So these are the rules that I pushed there. As you can see in this labs, I mean, it's step by step with every screenshot. Then I'm going to call a script set topology. This is just a script that will create Linux namespaces. So the goal is not to make you go over all the details every time you want to run it. You can put it in one script. Now, if you want to understand the internals of how you create namespace and you attach, the first lab in this theory will show you all of them in detail. But here we are just, because we are focusing on match action table, we're just going to call that script to create the topology for us. So at this point, we have that topology, right, that I was showing at the beginning, where you have a P4-DPDK pipeline and 2 devices connected to it. All right. Now we can test it. I will call here a script. It's just a Python-based scapy, right? You craft the packet that you want. And I'm going to execute it from the network namespace of host H1. So IPnet NS exec H1 means that I'm going to execute from H1's net namespace. That script is Python sender.py -s H1 -d. The destination is 192.168.10.10.2. And you see here, if you ever use scapy, this should be familiar, right? It's very simple. Now, if I go back to the first tab to see the pipeline, these are the logs that I was talking about, right? So you will see here, it told me here I extracted header 0, which is 14 byte. It's not telling me it's Ethernet header, right? But it's telling me the 14 bytes, which you can use to infer that this is Ethernet. Again, the logging is not great at this stage, but it's enough for you to get the job done. We extract 0, 1, 2. So we parse all the way to TCP, right? That means that maybe in that send.py, we already created a header that has Ethernet/IP/TCP. And then the table here, we have a hit. Why do we have a hit? Because we added that rule from the control plane. So because we have a hit, now we are emitting those headers, and then we are sending that packet out of port 1. So at least you know the packet was not sent. You know the table is hit. You know which actions were called, and so on. Any question? How are we doing with time? Okay, so that's basically a very, very simple lab. The second part of this lab is, what if you want to create a program where you have a table, but that table should be populated, right, based on the traffic. Think of stateful packet filter, right? You are sending a traffic from an internal network to external network. You want to allow the returning traffic. So you don't know initially what is the packet and the port number, all of this 5-tuple information. So there's in P4, only with this PNA architecture, there's a field called add on myths. When you add it to the table, it allows you to add an entry directly from the data plane. So you don't have to push it from the control plane. If you ever programmed in other architectures like Tofino switches, P4 programmable switches, it's not possible to add entries from the data plane. You always have to use the control plane. Portable NIC architecture allows you to do that. Okay? So for now, I think the remaining of this lab is very simple. I mean, you just continue by adding all of those and you can complete it. We can continue with this lab, or we can move to the other lab, which is, what was the second lab about? Yeah, we see how we can compute inter-arrival time and hash flows and do something a little bit more complex. What do you guys prefer? Do you want us to continue with this or jump to the next one? Next one? All right. So is there any question before we go to the next one? And I strongly encourage you, if you are interested in this, just keep doing the lab. It's as you saw, it's very straightforward. No questions? Okay, great. All right. So I'll go back to the agenda. And there's lab number 2. This is about computing packets inter-arrival time. We have to use here some constructs. One is registers. I will explain what that is, and also hashes. So what is inter-arrival time? Inter-arrival time is simply the time between 2 consecutive packets belonging to the same flow. Okay, you can say, well, I want it to be for any 2 packets not belonging to the same flow. That's also possible. It's up to you. But typically, let's say you have 100 flows, and for each flow, for every packet that you get, you want to know in nanosecond what is the time difference between the current packet and the previous. This is extremely useful for applications like identifying the encrypted traffic, detecting attacks, right? Again, because these, you can think of them as features you are computing in the data plane for every single packet. And then maybe you can pass them to some machine learning algorithm and do whatever you want there. Okay. But by knowing this stuff, I'm going to show you now how you do hashes and registers. This should be enough for you to use stateful packet processing. So you can store information in the data plane across multiple packets. You had a question?
No, that's all.
Okay. All right. So we will have multiple samples, right? Every packet that we receive, we're going to get a sample for it. Now, in reality, you have to make sure to have a plan on what are you going to do with those packets, right? Because you're producing a report per packet. What you can do, you can connect your device to a collector and send them all these reports, and that collector would have a history of all the inter-arrival times. Or maybe you can offload some of the logic and implement it in the P4 there so that you can compute the inter-arrival time and then take an action immediately. So it's up to you. Now, in order to compute things per flow, and this is something that is very important in P4 and in packet processing in general, you want to do some processing for a certain packet, for a certain flow, right? This means all the packets belonging to that flow will be treated in one way. Right? So to do that, first, what is a flow? Well, it's up to us to decide what do we mean by a flow. It can be simply a source IP, destination IP pair, or it can be the 5 tuples. And it's up to us to define that. Once we have access to those fields, which we already know by now that we can get the destination IP, so it's the same thing, you can get the other fields. You can hash them. So there's a built-in hash functions in P4, right? It's a simple hashing, it's not cryptography hashing, right? It's like CRC-based hashing. But that will give you a digest value that you can use to index that flow, right? So how does it work? I receive a packet. A packet comes to the pipeline. I take these 5 tuples, source IP, source port, destination IP, destination port, and protocol. I pass them to a hash. That's going to give me one value. That will be used as an index. Now, what you see here, this is a register. A register is different than a table in the sense that you don't have to do matching on it. It's just it's like a hash table basically, where you store some information indexed by a certain value that you have. In our case here, we are saying that the output of the hash will be the index of that table, and then the content, the value that's going to be there in the register, would be the last timestamp of that packet. So because here you can see that we are getting this for that flow, right? When you have a packet from a different flow, it will be going to a different index, and you will store the timestamp for that flow, and so on. With this register, you can put it like 65,000, 131,000. It's up to you. Okay, so now we store here T1. T1 is the timestamp. Now, in the pipeline, you can also call a function that will give you the current time in nanosecond. So we get that value, we store it in the register. Now, let's say we receive the second packet from that same flow. So it's going to hash to the same index, right? Because we're using the 5-tuple. There, we extract the previous value. We compute the difference between the two, and this is a sample of our inter-arrival time for this specific flow. Okay? Is that making sense? Now, after that, you can do whatever you want with that value. So the topology that we have looks like this. We have 4 devices, 4 namespaces, H1, H2, H3, H4. You have here, this is the pipeline, right? And these are the headers. So the sender, right? Let's say H1 is sending packet to H2. The sender here is adding a custom header called inter-arrival that we just created. The only reason we did that is just so that we don't have to deal with cloning packets and sending into a collector. This is for a different lab, but the goal here is not to make it too complex, so we focus on one thing at a time, right? So the packet gets from the device, it gets to the pipeline will insert the inter-arrival time that it got into this header. And then when it gets to the destination using SCAPI will extract that value and will display it. So we will test it with H1 to H2, so that's one flow, and then H3 to H4, that's another flow, right? And if we change the sending rate, we should be able to see differences in the inter-arrival times of the packets. Is that making sense? All right, so let's go to NetLab now. You can end the reservation that you have. You can create a new reservation. We have enough pods. It's a good idea to always, if you are not using, just end it. But for now, it's fine. So I'm going to go to the P4-DPDK library and select lab number 5. From there, I will make a new reservation. Allocate enough time, and then enter to the lab.
All right.
Yes. Yeah, that's a great question. So for these pods, because we use them in workshops and trainings and also provide training for students at USC, we make them non-persistent, meaning that, regardless of how much you mess up, you end the reservation, you get a new reservation, you have a snapshot from before. Now, for the research students that we have, sometimes they use this platform because we can add to it a P4 switch, a SmartNIC. I mean, you can add hardware to it. For those students, it's just a configuration. We say that we want it to be persistent because they want their files there. But for education purposes, workshops like these, yeah, you will lose your files. And we also do not have internet connectivity on purpose because, we don't want attacks coming to USC's network. Okay. Any other question? All right, so let's get started. I will, as usual, get the content, put it on the left, and then put the client on the right. Actually, let me do that. Just close this. Yeah, that's the problem of not ending the reservation, right? All right. So I will still have my reservation done, right? Because I simply logged out, it's still running. You don't have to recreate a reservation if you log out of the platform. All right, so I'll undock this. I'll undock client. Put one to the right, the other to the left. All right, so here is some background on P4 registers, right? So if you want to understand more how they work, how the syntax looks like, it's there. But we're just gonna jump directly to the code, and I will explain as I go through the code. So let's start by loading the environment as we did in the previous lab, and then start the lab directory here with lab 5. Now there, I will jump to the headers file and I will create a custom header, right? So last time we just used those provided Ethernet, IP, TCP. Now I'm going to create a new custom header. I'm going to call it inter-arrival, right? You can do whatever you want. You can create any kind of header that you would like. So the way to create a header is simply by writing header and then give it a name. And here it's mostly like a type because you're going to instantiate from that header later. So inter-arrival _T. And then you specify within that what are the fields that are part of this header. In my case, I only have one field that is the inter-arrival value, inter-arrival time value. So it's a bit 48 because with P4 you have 48 bits to represent up to the nanosecond granularity, right? If you say, well, I don't want to, waste that much memory, I want to store only in millisecond, then you can do a bit slicing, get rid of the nanosecond, microsecond, and get the millisecond. That's also possible, right? Okay, so bit 48 inter-arrival _value. So I just defined how the header looks like. Then I'm gonna make sure to add it to the struct headers. So these are the headers that are supported, right? There's already in there in the skeleton program provided Ethernet and IPv4. I'm gonna add to it now a new instance of my header, inter-arrival T, and then call it inter-arrival. Okay? Now, there is also in P4 the concept of metadata. These are data that would be available to you throughout the life cycle of a packet. So when the packet gets to your device, you can store some metadata. It's like variables in a programming language that you have to use for the life cycle of that packet, and they will be available to you. So you can add them here in a struct called metadata. Okay, they will be available through multiple control blocks that you have. Here we're gonna add these 4 fields. So the first one is flow ID. We said that we're gonna create that flow identifier to be 32 bits. Again, you can make it 16. It's up to you. Then we have here a timestamp value called last timestamp. So we created this timestamp as 64-bit because there is some limitation in terms of what is the width that you can support in this metadata. So you can 32, 64, 48 is not possible, but you can always cast later that 64 to 48. Okay? Then we would create one for the current timestamp. And then another one for the inter-arrival value. So again, notice this is not related to the value of the header, right? This is separate. These are just like local variables you are creating. All right. So now I'm going to save this file, Control S, and then move to the control block. This is where I'm going to write all my logic. So there, we already have a table for forwarding. I'm not going to be dealing with that. I just want to focus on the inter-arrival. The first thing we have to do is instantiate a new hash instance, right? So here, remember, apply is where you are invoking things, but outside the apply is where you are defining things, right? So here I'm gonna call hash, and this is gonna be a 32-bit hash here. That hash is gonna be the PNA underscore hash algorithm underscore T dot CRC32. So that's the hash algorithm that I will be using. It's already predefined. It's part of the PNA algorithm types. You have CRC16, you have some other hashes available to you. And then you give it a name. Let's say hash, simply. Right? Now, after that, I'm going to create an action that's called compute flow ID. So that's going to basically give me that index to the register. All right? Notice that it's an action. It's like really like a C function. You give it a name, let's say compute flow ID. I don't need any parameters here to that action. But inside the action, the actual implementation would be metadata.flow ID. Remember that metadata where we added 4 different fields? The first one was flow ID. So here I'm saying for that metadata struct, I want to fill the flow ID with which value? If I write here equal 5, for example, it's going to assign the value 5. But what I'm going to do, I will invoke this hash here that I created to actually compute the hash. So the way to do it is simply by writing hash dot get underscore hash. And it accepts 3 parameters. The first one is the minimum value produced by that hash. My register, let's say it's 1024, I can put the minimum to 0, the maximum to 1024. So the minimum is the first parameter, maximum is the third parameter. And the parameter in the middle, the second parameter, is a tuple where you can pass to it what are the fields that you want to hash. You want just to hash the destination IP, you want to hash destination IP and source IP, and so on, you place them there. So here we are not doing the whole hashing for the 5 tuple, it's just by hosts, basically. So we are hashing source IP destination, but it's the same, just add to it some other fields and it would work for the whole flow. So some functions which require you to have, to cast before you can place the value. For example, here we want to make sure to cast to bit 32, this minimum value 0. Then between curly braces, I want to hash the header IPv4.source address and the header.IPv4.destination address. Okay? Now the maximum is going to be 1024. And basically, that's it. So by executing this, let me just close the Explorer here. What we are doing, we are computing the hash. The minimum produced should be 0. And the maximum is 1024. The fields that I want to hash are the source IP and destination IP. And their value will be placed, the value of the hash will be placed in a meta.flow ID, metadata. It's like a local value. Okay? Now, I will create an instance of a register. So to create a register, you simply write register. And then you provide some information for that register. The first parameter would be here, the bit, would be basically how much data you want to store in each cell, right? So you want to store 32-bit values, 16-bit values, 64-bit values, you would place it there. And the second parameter is basically how big that register array is going to be. Is it going to be 16,000 different cells, 15? It's basically, this is what you define. Now, what we are defining here is how many bits to represent the length of the register, right? For example, if you write 32, you can have 2 to the power of 32 different cells inside your register. All right. And then this is here is basically where you are actually saying how many cells you want between the parentheses. So 1024. Now, here it doesn't make a lot of sense using 32 and 1024. You can optimize this further, but you get the idea. It's up to you to define the width. And then you give it a name. So we're going to call it register last timestamp. Okay. That's it. So now you have a register. It's there by default. It's initialized to 0. If you say I want to go to this register last timestamp index 5 and then place that value, you can store it, and that value will be used across all the packets. It's not limited to the life cycle of the packet itself. So this is where we now compute basically the inter-arrival time. So we need to have an action. We can call it get inter-arrival time. And we need to calculate to devise the logic here. So what is the logic? You need to get the last timestamp from the register, right? And that last timestamp should be for flow ID that you got from the hash before. Once you get it, you take the current timestamp from the device itself, from the data plane, you compute the difference, right? You get the inter-arrival value, and then you replace the last timestamp with the current time. So this is what we are doing in that block of code here. Okay, unfortunately, I can't copy and paste, so I'll have to type it, but I'll try to do it fast. Hopefully, I won't have a typo. So meta.last timestamp, right, is equal to register last timestamp dot read. I'm reading from the register now, right? And then you have to specify, because you are reading, where are you reading from? Which cell? So here's the index. The index is meta.flowID. So go to the index by flow ID, get me the last timestamp from there. And now, in the current timestamp, place the timestamp produced by the data plane. So bit 64, right? istd.timestamp. So what is this about? istd is simply, if you scroll up, if you scroll up, you see here that you have istd. This is the input metadata that is intrinsic. It's part of the device itself. So it's not the custom defined metadata, right? There are other fields other than timestamp available there. Okay. Now I want to create a condition to say that if the last timestamp that I just extracted from the register is not 0, because if it is 0, it means that that's the first packet. I cannot, compute the difference. It will be way off. So if it's not 0, it means that there's already a previous packet. Then I will update my inter-arrival value. Sorry, meta.inter-arrival value to be equal to meta.current timestamp minus meta.last timestamp. Right? Now else, if it is 0, if the last timestamp is 0, I'm gonna simply produce an inter-arrival value to be equal to 0, meaning that there's nothing before that, so I'm just gonna return the value 0 for that. So after I do that, I wanna make sure now to update the last timestamp to be the current timestamp now. So register last timestamp dot write bit 32 meta.flowID, and then current timestamp. So notice the read takes one parameter, which is where are you reading from. The write takes two parameters. Where are you reading? Where are you writing from, and which value you are writing? So I'm writing to the index of flow ID the value of the current timestamp. Is that making sense? Okay. Now, at this stage, if I compile and run, nothing will happen because I haven't invoked anything yet. So I need to add to the apply. So what am I going to add to the apply? First, I want to check if this is an IPv4 packet. So if header.ipv4 is valid, then I will check if the packet that's arriving already had an inter-arrival header, right? Remember, I said the sender is going to be inserting that header there. So I will check here if header.ipv4, if header.interarrival is valid. Okay, what am I going to do if I want to compute the inter-arrival time of this flow? First, I need to compute the flow ID. So I will invoke the action that's gonna be filling that meta.flow ID. So the action is gonna call the hash. It will take these parameters, give me a number, place it in meta.flow ID. Then I will call an action, get interarrival time, what we just implemented here, right? So that I can fill my meta.interarrival value. And once I have meta.interarrival value, I have to place it into my header. So header.interarrival value is equal to meta.interarrival value. Think here there's a typo, it should be meta.interarrival value, right? And if you look at the screenshot, right, it shows you the right syntax. So we need to cast first, right? So bit 48, interarrival value. All right. Any question? We did a lot of typing. Hopefully I didn't do any typo, but should be able to trace it back if I have. So make sure to save your file before you compile. So to compile the program, P4-DPDK -- architecture PNA, main.p4, the output is lab5.spec. Okay. Okay, so this is something interesting. It told me that I have a warning, so it compiled successfully. But the warning is you created a table forwarding, but you never invoked it. So if I go back to the last step, you can see here after the if statement, I forgot to add the forwarding. So it's not that bad. I mean, it told me that I forgot something. So forwarding dot apply. And now I will compile again and it went away. Okay. Any question? Now the next few steps are just to deploy the pipeline and create the namespaces and attach them to the pipeline. So similar to what we did in the previous lab. I'm gonna go to my terminal, go to super user mode, and then go to lab5 directory. From there, I would run the pipeline. All right, notice here I have now 4 devices connected to it. Right? Remember the topology, we have 4 devices. And then I will open a new terminal. I will keep the first one running. And from here, I'll also go to the directory of the lab, so lab5. And from there, I will set the topology to create the namespace and attach them to the pipeline. Now we are ready to test it. So the way we are testing it is we're gonna generating packets, right? And we're gonna see what Scapy is seeing at the end, right? Because remember that interarrival value is being placed into the headers. So I will first start Scapy, so it's just sniffing on the packets. So IP net NS exec h2 Python 3. There's a script that we wrote called receive.py. It just received the packet and displays the information about the headers, basically the header content. And then -p interarrival. This is just something so that we can use the same script across all the labs. It has nothing really meaningful here. But assume that you have a Python script, you are sniffing packets. That's it. Okay, so sniffing on DTAP1 and sniffing on the interface. Now, I will create a new terminal. Go to super user mode. And then go to lab5. And I will start sending packets. So I'm sending from H1 and I'm sniffing on H2, right? So IP net NS exec H1 Python 3 send.py. You give it the destination IP address, so 10.2. Now here we have a new parameter, 10-p enter. All right. So this 10 here is basically specifying how many packets per second you want to send. I'm saying here I want to send 10 packets per second, right? So if I'm sending 10 packets per second, how much the inter-arrival time would be. So 1 second you divide into 10 packets, right? And you see here, okay, you have 100 milliseconds, because 100 millisecond times 10 is 1 second. So I'm reading all these values here, and they're around 99 milliseconds. I mean, it's not going to be 100% accurate because this is software, right? But we're getting around 100 millisecond inter-arrival back. Okay. Now, if we run that same code, if we can keep this running, right? And then we open a new terminal and we run the same thing, but from a different device, right? Remember, we had the topology, it has 4 devices. So we use the first 2. Now I'm going to use the bottom 2. If you run that and you change the inter-arrival time, like say 20 packets per second, so now your inter-arrival value would be 50 milliseconds. And you can test that and it will show you 50. So it's basically doing it per flow. It's replacing the, this one will still be running, and then you will get, just to show you that you are doing things per flow and not you are computing for all the packets. Okay. Is there any question? Okay. So I will not continue the last part. It's just for debugging, but you get the idea. It's just instead of getting 100 milliseconds, you will get 50 milliseconds. Yes. Say it again. One thread processing one flow. So basically, all of this pipeline is running on one thread, right? That whole pipeline, one thread. And the packets that get to that thread, if you have a physical NIC, they're defined by the hashing within the NIC itself. Because, let me show you here. So I will go back to the agenda. So okay, so here the NIC has this hardware-based classifier. Some of them would allow you to configure that, right? But here, essentially, what we ran is on one CPU core. So all the flows that are getting to that physical NIC would get to that. Yes. Now, when you run it with a physical NIC, you can say, I just want one pipeline, and all the packets will get there, right? Or you can split it, so it's up to you. But one flow passing it to a pipeline, that only works if you can control here which queue to use and then create a P4 code different for that pipeline. And by the way, you can create different P4 code, compile them separately, generate the different spec files, and then say CPU core 1 will run P4 code 1. Core 2 will run code 2, and so on. They don't have to be the same code, which is very interesting because now you can do a lot of things, right? When you do it that way. Okay. And also you can chain those pipelines. So let's say you can have a P4 code that's doing a specific function. You put it in one, on one core, and then after that whole pipeline finishes, instead of sending out of a physical port, you can send it to another pipeline as an input, and then you can parse again and do whatever you want. So it's very flexible in that sense. And really, I mean, you would get all the benefits from it. In the morning, we were talking about, Kubernetes and Dockers and stuff. This is with DPDK, right? You can use SRIOV or pretty much technologies where you can connect your VMs or your containers, right, to this pipeline. So that port 1, instead of going to namespace 1, it will go to VM1 or VM2. See what I'm saying? So that's also possible. Yes. Yeah, well, so the added value would be that you are doing per packet processing, right? You express it in P4 and you are bypassing the kernel stack. So the performance that we saw. Now, when it gets to the pipeline, right, there's something called virt.io, right, that you can use to connect VMs and containers to DPDK pipeline. And that also is performant. So you can get good performance as well. Now, in terms of which one is faster or like benchmark, I don't have these values. But for sure it works and you will get good performance with VMs as well. And remember that this pipeline, you can also run it on the CPU cores of the NIC itself if it has CPU cores. So now think of it as a switch running on the CPU core for your VMs running on the hypervisor on top of it. Yes, yes.
It's like I was working on
Yes. So yeah, it's interesting that you mentioned 5G. They are doing some stuff for, per packet processing on 5G traffic, like GTP, encapsulation, de-encapsulation, stuff like that, NGAP, parsing these protocols. That's possible. I mean, there are some vendors that are also now providing solutions where you have that already implemented in the smart NIC itself. The use case is really based on the business itself, but you can do a lot of things in it. It's up to you how you program the pipeline. Yes. Yeah. Yeah, so as long as the packet gets there somehow, like you can basically force it. For example, to give you an idea, what we have in USC, we have, our research network that we just create like a testbed for experimentation. We have optical taps, and then we deploy them so that all the packets go to a P4-to-Fino switch, right? You can forward those packets to a P4-DPDK pipeline and do whatever you want there, like profiling, count how many flows you have, what is the size of flows, and all of that fun stuff. So that's possible. And from Princeton, I know they're doing a lot of things with tapping and get traffic and summarize things in P4 and do a lot of applications. So yeah, it's doable as long as you know how to get the packets there. It can be port mirroring, it can be tapping, but essentially it only operates on packets. So something like CPU usage, stuff like that, that's not gonna be available to you in the pipeline. Okay. Any other question? Those are very interesting discussions. So we still have around 20 minutes. We're not gonna have time to go over the last lab. However, I will talk a little bit about this lab specifically, which I believe a lot of you will find interesting and might be interested in deploying it. What we saw so far was running DPDK pipeline on a virtual NIC. If you are doing research, you want to test with high-speed networks, that's not going to be very useful. You want to do it with a physical NIC. So if you have a NIC yourself, let's say a ConnectX, Intel NIC, you can run all these codes and they would work well. What we did, we have basically accounts on Fabric. So Fabric is a test bed. It's funded by the NSF. It has nodes across all the US, and also it has nodes international. So basically you can run an experiment by selecting which nodes you want, get the resources, say I want, let's say 8 CPU cores, 20 gigabytes of RAM, whatever, you decide those, and then you would run the experiment that you want. Now in Fabric, there is NICs that support DPDK. So you can do these tests that we were showing and then test them at high speeds, all on Fabric. Or of course, you can do it at your own network if you have those NICs. Now, what exists in each node in Fabric? So you have CPUs, GPUs, storage. There's a lot of interesting research happening there. Machine learning, getting scientific data from an instrument and process it. A lot of interesting research with networking. Now they're gonna add also P4 programmable switches, like P4-to-Fino switches that would be available for you to run experiments at terabits per second scale. So it's really interesting. We at USC, we also got a grant recently where we're gonna also add some smart NICs to Fabric. So there will be FPGA-based smart NICs. There will be also NVIDIA-based SmartNICs, Intel SmartNICs, and so on. So this is going to happen in the next year or two. But essentially, you can see this is a summary of the resources available on Fabric. There's really a lot. I mean, 87,000 CPU cores. I don't know how many gigabytes of disk, 60,000 gigabytes of RAM, and so on. And that's all virtualized. So you decide, I want to use that, and then it's going to be allocated for you. We created a library for this P4-DPDK over Fabric. So if you want to learn exactly what we were doing here on the virtual NICs, but you want to do it with physical NICs, you can go over these labs. The last lab will show you how to run it with multi-core processing, right? So the first labs are on virtual NICs. Even on Fabric, they are on virtual NICs, just so that we can see the logs. Once you are done with your program, you're ready to deploy it, you go do the last lab that will show you how to run it at high speed, right? Because you deploy it over multiple CPU cores. Now, what is the interface on Fabric? It's Jupyter Hub. So you have the code, you have screenshots, you execute the cells separately, and then you get the experiment done. You have more than 15,000 NICs that all support DPDK. So it's really scalable. You can all do experiments without having to do anything special in there or requesting permissions. This is a lab, right, for detecting SYN flood attacks. So what is the idea here? SYN flood, it's a TCP attack where, we send a large number of SYN packets to a server. That server will keep those SYN packets, and then eventually it's going to run out of memory. It's not going to be able to basically respond to legitimate SYN packets, legitimate clients. So we can basically detect that in P4. One example of a detection logic, there's plenty of them. You can count how many SYN packets are per second, right? And then when that number exceeds a threshold, you can start dropping those packets based on some probability. That probability can be configured, let's say 50%, 80%, 10%. It's up to you. Okay. So this is a simple logic, but you can implement it in P4, and that would work at 100 gig rate. Okay, this is showing an example here. So if we set, let's say, our threshold to 100 packet, this is just a simplistic example. And if you are receiving 900, then anything beyond the threshold, which is 100, right? Meaning that the remaining 800 packets, okay, we're going to apply the dropping percent to them. If our dropping percent is 50%, then we're going to get half of them, meaning that 400 plus 100, you're going to get 500 packets. But this is just a simple logic, but you can make something a little bit more complex and do it the way you want. So this is how it looks like. You have a pipeline very similar to the topologies that we've been seeing before. I'm going to go over the notebook. We're not going to have time to run it, but I will just show you there, and then I will show at the end a demo where you can see that running in real time. This is a slide. If you guys are interested to have access to Fabric, and if you are doing network research, I strongly encourage you to get access to Fabric. Now, if you are a professor or a researcher, what you have to do is you have to create a project. That project will be approved by the Fabric team, but typically they approve all projects as long as you are working and you have a title, and there's like a public URL that shows your name there. And then if you are, let's say, a professor, you can enroll students to your project, and then they will all be using that Fabric testbed and do all the experiments that they want. They've been using it for teaching, networking, for doing a lot of fun stuff. I mean, I use it a lot. All the research that I'm doing, if everything is available on Fabric, I will use it. So it's really powerful. So I just put here some links. So if you want to create an account and if you want to create a project, and feel free to do so, they will be very happy, the Fabric team, to support you. There were some talks, I think, today and tomorrow on Fabric security. So it's pretty big, this project. Now, what I'm going to do next, I'll just show you the notebook. So Samia, I will stop sharing. I will show you now the interface to Fabric, how it looks like. And you will get an idea of the labs if you want to run them. All right. So can you see well? Okay. So this is an example for that lab that we were talking about, right? So what you have first is introduction, the lab scenario. Now, the way you execute here is a little bit different because this is a Jupyter Hub, meaning that you have cells here. You go over each of those cells, right? Let's say this first cell here, you click on play, that would execute the cell. First, you start by including some libraries, and then you create a slice. For that slice, you say, well, I want 3 servers, server 1, 2, 3, for example, right? Then for those, you can decide what type of NICs you want. For example, I want NVIDIA or Mellanox Connect X6, which is 100 gig NIC. You do the connections, right? And then you submit the slice. Once you submit the slice, you will have here the SSH commands to access all these devices. So you can now log in, and basically what's interesting about it is that at the bottom, there's a lot of networking happening. If you remember that figure of fabric testbed has a lot of nodes interconnected. For you as a researcher, like from your perspective, you see it as a L2 network between 2 devices. So it's really abstracting all the lower layer. You can have an L2 network, have your own LAN, and then ping, you can create VLANs. So it's really virtualizing all the network on top. And this is great for research because you want to run experiments. For example, I want to test congestion control in TCP. I want real propagation delays instead of emulating ones. I can use this and get much more granular and results with more fidelity basically than doing emulation. Okay, so once you have that, you're gonna get fresh Linux machines. You can select Ubuntu, Rocky, whatever you want. And from there, you can start doing basically whatever you want. Now here, we are using P4-DPDK. So the first few parts of it is installing the dependencies to compile P4C, to install the Mellanox drivers, install DPDK, and so on. Packet gen to generate packets. Then you can reboot them to make sure all the libraries are loaded and everything is fine. You can get the interface names, turn them up, assign IP addresses. If you really look what's happening in those cells, right? I'm writing sudo ifconfig interface name. It's like you're running Linux. So what's good about Jupyter Hub is you can write basically your experiment, save it in a file, right? And it's reproducible because you can simply want to rerun it, you play from installing the dependencies, creating the VM, all the way till you get to the result, right? Now, that doesn't mean that you always have to write it in Python like this. You can open a new terminal, like the ones that are there, right? And then interact directly with the VM. Okay? So now we have everything ready. We start implementing the P4 code. We are doing here the logic that I was talking about, the SYN float, right? So we provide the starter code. It's part of the package that you will get access to once you enroll to Fabric. We are working with the Fabric team so that all these labs will be automatically pushed to all the users, right? As long as you have Fabric access, you can use those labs. And it tells you, well, click on the control.p4. If you click on it, right, that would open the P4, like a text editor there where you can do the mods there, modifications. And then, same as before, where you see that red square, this is where you type. And here is, we are implementing the logic for the SYN float detection, right? So you create a register for the dropping percentage and another register for how many SYN counts have you received. It's just a counter, basically. You keep incrementing by 1 every time you receive a SYN packet. Now, I was just gonna scroll down and show you the whole code written and go over it really quick. Okay, it should be here. All right, so if you see here, you have the first step is, if it is an IPv4 packet, you apply forwarding. If it is a TCP header, you read the dropping percentage that the administrator configured, 50, 30%. Then, if the TCP flags is equal to 2, meaning that this is a SYN packet, right? you initialize your SYN counts to 0, you read it from the register. Notice here, I'm reading from index 0 because I don't want to track things per flow. I just want to have a register that tracks the total SYN counts, right? So I read it, I increment it by 1, and I write it back. So I'm just incrementing and rewriting here. Then I check if the value is greater than a threshold that I defined at the top. If yes, what I will do is I have a percent iterator. The idea is as follows. If I said I want to drop 50% of the packet, I can create an iterator that will increment from 0 to 100. If it is below 50, I drop all these packets. Once it exceeds 50, I will allow the remaining traffic or the remaining packets. That's just one example of implementing it. So this is what we are doing here. You'll end up with a code that has all these if statements and incrementing and writing back to registers. But it's not hard. I mean, it's really simple. You just track the counts and then you drop. Now, once you have it ready, you upload these files to the VMs and then you issue the P4C to compile. You see here the P4-DPDK that we were doing in the lab is there. Then here we want to run that pipeline on 4 CPU cores. So I need to have 4 different files. Each of these files will contain basically the queue number. So the PCI address, let's say, is 070000. That's the physical, PCI address. And then for that address, I have Q0, Q1, Q2, Q3. These are my 4 queues. So all of those are within that file. You reserve huge pages. This is mandatory for any DPDK-based application. And then finally, you can run that and test it with high rates. So I'm going to let Samia demonstrate this. You can control this, right? You have to come here to speak. Yes.
All right, so I'll have to go back to this step. So as you remember, so once we created the slice and we assigned the nodes, the VMs were created, and for each VM, an SSH key has been assigned. So we have an SSH command that we can use to access each server. And we have 3 main servers. So server 1 is going to be the attacker. So it's going to be sending SYN packets at a very high rate. Server 2 is the server on which we are going to be running the DPDK pipeline. And server 3 is the victim. So we are going to see if server 3 is going to successfully limit the rate at which the attacker is sending these packets. So I'm gonna have to.
You can just demonstrate something because we're running out of time. If you can just run the
Sure. Okay. So on server 2, we are going to be running the pipeline. And over here, you can see that we have 4 pipelines running. Pipeline 0 through pipeline 3. And we are going to be resetting the count of SYN packets every 1 second, so that we will be getting the per second packet count. So this code is just setting and writing the value to 0 in the register. And on server 1, I am running a packet generator. It's packet gen, and it's also powered by DPDK. So I'm gonna start sending packets. So if it would be better if I can put them side by side. Okay. And we'll be inspecting here server 3. So this is just to tidy up the interface, how it looks. Okay, so by issuing the command start, I will be running packet gen, and I will be sending packets at a rate of 100 gigs, but I will be also sending packets from a range of flows, not from a single flow. So we can see that packet gen is generating packets and sending them. So that's the TX. So it's sending these packets at 100 gigs, which is equivalent to 8 million packets. And the victim is receiving them all. So it's receiving also 8 million packets at a rate that is equivalent to the sending rate almost. So we can see that no rate limiting is applied. And this is because initially the registers assigned are filled with zeros. So we will have to write a value to the register. And to do so, we are going to do it in the control plane. And to access the control plane, we are going to open a telnet session. And this is where we will have to pass the commands. So luckily here we are able to copy and paste. So we have done all of these steps. These are the steps to run packet gen and to configure it also. Okay, so this is also about running packet gen on the victim. All right. So I will have to copy the following. And paste it right here. So over here, you can see that at pipeline 0, I am writing the value 50, which is the drop percentage now, to the drop percentage register. And this is something that you can see in the spec file. So once we compile from P4 to DPDK, the P4-DPDK compiler ends an _0 at the end of the register. So to be able to access the register, we will have to edit it here. And we will assign the value that we want to write, and at which index also of the register we would really write to insert this value. So I'm going to do this for all pipelines.
So notice how it's creating registers for every pipeline, separating them. So even though it's the same register name, right, it's not shared among all the pipelines, creating 4 different registers, and then you have to set the values for each because, you know, they are isolated. That's the same for tables and all the other elements. So that's why we have here 4 items, right? We're running on 4 pipelines, so I have to set the 50% on the 4 registers.
Okay,
Set it to 100.
I will rewrite.
It's fine.
Okay, so there's one that I wrote a value equivalent to 100. I will rewrite it or overwrite it by 50. Okay, so now if we look at the packet generator, the packet generator is still sending packets at 100 gigs per second. But the receiver now is applying rate limiting, and instead of receiving all 8 million packets, we are only receiving 4 million packets, and the rest is being dropped. And where is this being dropped? In the pipeline. So the pipeline is dropping the remaining 4 million packets. And if we want to drop all packets from the moment at which we exceed the threshold, so eventually we will only be receiving packets that are specified by the number or by a number which is the threshold. So we can go ahead and set the drop percentage to 100. And that means so every packet that is received after exceeding the threshold, it's going to be dropped.
Okay, so meanwhile, this is very similar, but you'll end up dropping most of the packets here. We're running out of time, so first I want to see if you guys have any question on everything that we covered so far. Was it useful to you guys, all the stuff? Hopefully. So what I want a favor from you guys, if you can fill the survey. So the website, we're gonna send that link again through an email to all of you who registered. But there's the website that I showed at the beginning of the slides. At the bottom of the agenda, there's a survey. We would really appreciate if you can fill that because we use this information to improve every time.
All right.
And other than that, I hope you guys had a
We can
fun
see
time doing
it.
this. And now we're seeing you can show Samia.
Yeah, so instead of receiving also all the 8 million packets, here in the P4 code, we have specified the threshold to be 1 million. So only 1 million packets are allowed and everything else is going to be dropped. And regarding also the survey, there is something that might be a little bit less of a hassle for you. So you can also scan this QR code and do it right away. And if you have any questions, we'll be waiting right here for you.
And by the way, the recording for this would be also available. So you can go back over them and the labs would be available for 6 months. You can get more time if you want. And if you're interested in other labs like P4-BNV2 or other stuff as well, just let us know, we will enroll. Yes. Yes, all the labs have the very similar steps, screenshot, so you can do it all by yourself. We don't provide certifications. However, for some of the libraries that we have, for example, I just want to show this real quick. So this lab library, let's say cybersecurity, right? So we created here around 20 labs on different topics, from reconnaissance, creating a Trojan, escalating privileges, spyware, SQL injection, cross-site scripting, all these topics. Very similar to the format that you guys saw. So you have steps and you do it, and all of them are guaranteed to work. Now, these labs are following the content of the CompTIA Security Plus certificate. So if you study for that certificate, you want to do the labs, you can use those labs to basically understand more the concept for that certificate before you sit for the exam. And we have other libraries that are, more networking focused, other more measurement focused, and so on. Okay. Any other question? Well, thank you so much for coming.